Hi, welcome back to Act 2 of JAX. This is Lecture 8, High Static Arguments. So all of Act 2 of JAX has been about learning how to just-in-time compile our programs, and that has involved learning how to sort of fit our programs into the shape that works well with the just-in-time compilation workflow in JAX. So we've got the tracing and then the compilation and then the execution. And one of the biggest restrictions that our programs have to conform to in order to work with just-in-time compilation is that the computational graph of our program isn't allowed to depend on the values of the arguments to our function. It's only allowed to depend on the actual shapes and data types of those functions. But sometimes it's quite natural to want to write a program where one of the inputs determines the course of the computation or the shape of the computational graph. In order to be able to write programs like this, we need a way to tell the just-in-time compilation transform that these specific arguments are going to be ones that you're allowed to assume that you know them at compile time, and you don't have to trace through with an abstract version of them. And these are called static arguments. So today's lecture is going to be all about static arguments. We're going to start in the JIT dojo, learning a little bit about static arguments, and then we're going to come back and implement a small transformer, not a large language model, just a small transformer that's going to be trained on a small text data set. And this will give us lots of chances to explore static arguments and computational graphs and just-in-time compilation in JAX. So the only difference in the environment setup today is that you might notice the host name has changed from my normal MacBook Air host name to I'm now running on a TPU node provided by Google's TPU Research Cloud. So this is the main purpose of this is we can run this transformer. It's going to be a pretty small transformer. We could run it on my laptop. When I'm not recording, it takes like longer to train than any of the models we've done so far. I'm just a little worried that it's going to overload the recording software. So I've moved to the TPU for today, and which will also make things run like way faster, and we'll get sort of a better feedback loop for the demonstration purposes. But I'm just in the JAX repository, which you can find on GitHub. I'm in the JAX virtual environment, same here as before. I think I'm using maybe a slightly different version of Python here, but it should all still work. So let's go into the JIT dojo and get started learning about static arguments. So we've so far in previous lectures looked at lessons 0 through 4 inclusive, and today we're going to look at lessons 5 and 6. So let's start with lesson 5. And I can also run this. I just have a note to self. I have to run with my little shell shim to make sure this runs on the right part of the TPU. This is not really an important detail at the moment, but I have like a TPU here that's networked with some other TPUs, and if I don't include this, then it's going to try and run it in parallel over a bunch of TPUs. I don't want that. I just want to run on a single 2-core chip of the TPU. And so we should be able to run this and then get some outputs. Okay, so this lesson is about static arguments or static parameters. So we're going to do this kind of thing that we do normally. We're going to define a function, and then this is a function that doesn't have any JIT going on. It's just running in like pure JAX without optimization. And it's a function that takes an integer input and then returns an array that has that input as the shape. So this is the kind of thing that you might like to do. An example of a function like this would be jnp.I, as in EYE, which you would give a number and it would give a diagonal matrix back with the identity matrix with that sort of size determining the shape. But this is a classic example of where we were going to need the input to our function. We're going to need to know that in order to determine the shape of our computational graph, because even the return value itself is going to depend on that shape. And so let me see. If we run this function, we transform it, and then we call the function, what's going to happen? Okay, you know what? So here I've defined the function. That's okay. I have transformed the function, and I've done a new thing here where I've said, okay, I want to mark one of these arguments as static. And I just want to show you what I've got as a comment here. Without static argunames, this is going to raise an error. And this is an error that we will have seen before. So I want to show you that error because you'll see this many times. Okay, so it's a concretization. Excuse me. It's a concretization type error. So JAX is telling us that an abstract tracer value was encountered where a concrete value was expected. And that's in a traced array with shape int32. That's what was found. It arose in the JNP arange argument stop. Okay, so where are we? In the function, we have JNP arange. we have this n parameter being passed in. And this A range, this is the stop parameter of A range. It's going to tell us how far to go with the A range. And of course, we can't know what shape the output of this operation should be without knowing what n is. And so hence the error. We need a concrete value rather than an abstract value. And let's see what it tells us. This concrete value is not available in Python because it depends on the value of the argument n. So yeah, I mean, that basically tells us all we need to know, and you'll learn to recognize this concretization type error as flagging that you're going to need to mark something as static. So the way we can mark something as static for JIT is to pass this static argnames. And that is going to basically say that we want you to transform this function, but when you get up to the argument n, don't replace that with an abstract value. Just use the exact literal value that was called in the function instead. And then we will trace through and there would be no problems. So if we go back to this version of the lesson and we run it, again, we're going to see that it transforms with no problem. And then, in fact, it calls with no problem. And when we're tracing, this is crucial. When we're tracing, we can see n equals 4. And so this was, this wouldn't have been the case previously. Previously, when we were tracing through, we would have seen n is a JIT tracer of an int32. I guess it's using like a weak type here. It doesn't know exactly that it's an int32 because it was a Python integer. And it could like coerce that later to something to make it all work. And that's what the tilde means. But at the moment, it's the key thing is that it's a JIT tracer. Whereas when we run this with the static argnames keyword argument to the JIT transform, it knows that it's a concrete value of 4 instead. And so this is basically how we get values into our programs at trace time. It's using the static argnames function. All right, let's see what else we've got going on here. So I guess the rest of this is not going to be super surprising. What we actually do is, apart from these printing commands and so on, we are going to build an A range from 0 to n-1 and then add 1 to it. So we get from 1 to n. And then at trace time, we're going to see what we know about that. So at trace time, we at that point just know that this is a, oh, sorry, I'm in the wrong place. At trace time, we just know that this is a JIT tracer of a particular shape. It's an int32 array with 4 elements, sure. And then we're going to diag that array. That's going to turn it into a diagonal array with the values here, or it's going to turn it into a matrix, I should say, with the values here along the diagonal. And then we're going to return that, and that's going to satisfy the contract that we set up with this type annotation here. And it's almost like the identity matrix, actually, but it's going to have increasing values going down the diagonal, and that's the value that we're going to get. And then we see this result. Oh, sorry, I guess I'm failing to distinguish between trace and debug, but we've seen a few of these now. I think we get the idea. So here's something interesting, actually. At debug time, these print statements have come out of order. And so I guess that's something to keep an eye out for. That because of just the way that JAX handles things internally, it doesn't guarantee that things will happen in the same order as what they say in the program unless the values depends on this. So you might sometimes see these debug print commands execute in different orders. And so it's always a good idea to sort of include information in the string about like what the value you're printing, because if we had have just printed a sequence of values, it might have been a bit confusing why we got the array before the number. So that's something to look out for. But then yeah, anyway, we see the concrete version of this at debug time or at execution time is like we expect. Okay, so if we let's continue to work this into our understanding of how JIT functions work in JAX. So the next thing we do is we this is the first time we've called the function. Let me see. Could we call the function again? Okay, well, maybe we would know that if we would call the function again with the same values, we should get, or with the same shapes and data types, we would get the same output, but it wouldn't trace. However, what we're going to see here is if we call the function again with a different value of the static argument, then it looks like it does trace. So calling the function again, but this time the n value is 3, and what that's going to result in is printing tracing commands again. So it looks like we're tracing through again. And this makes sense intuitively because once the static argument changes, since the computational graph is allowed to depend on that, we're going to need to trace again and because we might have a different computational graph. So that is generally true, is that when you provide a function with a different value, so we previously learned that when you provide a function with different shapes or data types on the inputs of the what we'll call dynamic arguments, the non-static arguments, when you provide the function with different versions of those, it's going to trace again because it's using the shapes and data types to determine whether it's already compiled a relevant computational graph or not. But in this case, we're seeing that if we provide a different value of the static argument, that's also enough to trigger a recompilation or a retracing and a recompilation. And that makes sense because the static arguments are allowed to determine the shape of the computational graph. So if we change the value of the static arguments, we can't guarantee that we have a ready computational graph, even if we've already executed using the same types and shapes of any arguments that do have shapes and types but are dynamic. And so, yeah, that's an important thing to keep in mind. Okay, I think we're ready to move on now to the next lesson. So let me quit out of this and open up lesson 6. So lesson 6 is a little bit longer, but it's not that much more complicated, and it's just to make, we already sort of have the basic idea. I think this is just to make a further point. So I'm going to keep my TPU device 0 shim and then run lesson 6. And this lesson is called Only Some Types Can Be Static and Only Some Types Can Be Dynamic. So, okay, so we've got another function here that we're compiling, and we're jitting it with static arguments as a decorator this time, rather than defining no-jit and then defining jit later. And the way that we do this is with functools partial, and that allows us to call jax.jit partially at the time of the decorator, defining the decorator, saying this basically functools partial is going to give us a version of jax.jit that already has the static arg names provided. And then we're going to use that as a decorator, and that's going to decorate the function so that when the function gets defined, the jax.jit that gets called as the decorator already has the static arg names argument provided, and that's going to get plugged in. And so that is, I suppose, what you would expect. Now have a look here. We've got a function with n and a again, and n is an integer, which we're going to want to mark as static, and a is going to be a dynamic input. We're going to care about the shape and the data type, shape and data type. So this is going to be according to the type annotations, although not necessarily in our actual practice, an M array of integers. And then the output is going to be an integer array of size n. That's allowed because we marked n as static. So let me see. We're going to print out these inputs, what we know about them at trace time and then at compile time. And then it looks like we're just going to run an addition operation. So I guess this is actually a bit of a typo. This should probably be m, because it looks like what we're doing here is we're taking an int array of length m and we're adding an integer. So broadcasting is going to allow this to happen. And our computational graph isn't so much going to depend on the value of n in this case, but that's okay. We can still mark it as static, and it will just be a little bit redundant. But anyway, we're going to be adding, this would be like saying, take my array of length m and then add a constant to it. That is going to use broadcasting to add that constant element-wise to all of the elements of the array, and then we'll return that. And so let me see. So we've defined and transformed the function, so we've got our pjit function of the function. It's going to have the static arguments flagged, because we use this functools partial. This is a very common pattern in JAX. Okay, so calling the function, it looks like at trace time, as we would expect. Where's the call of the function? So we've called the function with n equals 10 and a equals a range 5, so 0, 1, 2, 3, 4 in an array. And so at trace time, we've got the value of n available, and at trace time, we also know the value of a. We don't know the value, but we know that it's int32 of shape 5, and we just got an abstract tracer here. Something else has happened here with the order. I wonder if this is happening on the TPU more specifically because of the way that I've sort of set up these, because of the way that I'm using SSH here. But I'm getting some out-of-order printing here, and I'm not exactly sure what's going on. But it looks like maybe while it was printing out the result, we've printed out that the fdebug is n is 10, and at execution time we know that a is 0, 1, 2, 3, 4. And then it looks like this must be the result here, that we've printed out 10, 11, 12, 13, 14, which is indeed 10 plus this array. Okay, so if we call the function again, this is just like last time. If we call the function again with a different value of the static argument, even if we use the same shape for the dynamic argument, it's going to trace again And so we're going to get now a new computational graph that says that constant that you should add to the array, that's actually 11 now. This is, it doesn't have to be a computational graph, because you could have had a computational graph that said, add this abstract integer to this array, and you still have the broadcasting and everything, but we marked it as static, and so we're getting a recompilation here. So we get what we asked for. Okay, so this is so far the same as we sort of expected. However, I'm going to do something different now. And remember that these type annotations are just for us, and we're never actually checking this. I believe, to be fair, JAX typing allows you to do some runtime type checking, but I'm not using it at the moment. I'm just using this for us. And so what we could do is we could say, well, what if I do want to provide a NumPy, or sorry, a JAX array as the input 1? Well, that's actually going to create a problem. And so let me show this error and then explain what the problem is. So in this for, only hashable types can be passed as static params. And so I'm going to try to call my function with n, instead of being an integer, I'm going to call it with an array, which is not generally a hashable type in Python, and in JAX specifically. And I'm going to get an exception, and I'm going to print out that exception. Let's see what we get. Non-hashable static arguments are not supported. An error occurred while trying to hash an object of type class JAXlib JAX array impl 1. This is the printed version of the object, I suppose. And the error was type error unhashable type JAXlib JAX array impl. So I mean, it's sort of going on and on, but it's basically saying that it tries to hash this object that we pass in, and it gets an error, and then it's telling us that non-hashable static arguments are not supported. So why might that be the case? Well, think back to this idea of having a compilation cache. That cache is going to be basically implemented as something like a dictionary, as in a Python dictionary. And we know that Python dictionaries have to have hashable keys. And so what you can think of is, imagine we have the compilation cache formatted like this. So every time you call the function, I'm going to look at all of the shapes and data types of all of the dynamic arguments, and I'm going to look at the values of all of the static arguments, and I'm going to use that to get a sort of a signature of the function that I might represent as like a tuple or something like that. And then I'm going to use that I'm going to hash that and use that in a sort of a dictionary lookup, but in general, I'm going to use that as a dictionary key to store all of the information associated with that trace. So I'm going to store the computational graph and then the compiled JAX program that I would actually execute if I ever see that combination of inputs ever again. And so we do see that combination of inputs. If we saw that combination of inputs again, we wouldn't have to compile again, and we can skip the tracing and compilation step and go straight to execution after we've done this cache lookup. But this cache lookup is going to involve hashing, because internally dictionaries, or whatever JAX is using internally, I'm not 100% sure that it is dictionaries, but presumably it's something like that. And evidently it requires the things to be hashable. So this is not going to work. And in general, this is why you can't use hashable types as static arguments. You can. There's nothing actually stopping you from saying that this is an int array and then saying it's also static. But we see that when it comes time to look, we know this is sort of just defining a function and sort of what arguments to put in the cache key versus replaced with traces, abstract versions. And so when we get to this point, instead of looking up the data type here, we told it this was static, so it's going to try and hash the value and make it part of the cache key, and it's going to fail. Okay, so what else can we learn about JAX? So the last thing to learn about static arguments, this is actually not about static arguments so much, or kind of is, but it's more about dynamic arguments. And that is that only JAX arrays basically, and pi trees of JAX arrays can be passed as dynamic parameters to a function that we're going to JIT. And so let's see what we're doing here. Here, we're just completely ignoring the idea that, okay, so actually, first of all, this function, if we hadn't JITted it, would have worked in this case. If we had have passed an array 1 and an array of a range 5, this would have worked because of broadcasting. You can add these together, no problem. You can also add two tuples together in Python. If I have a tuple that just contains two built-in functions, min and max, and another tuple that just contains a, let me show you. In Python, there's nothing stopping me saying min, max, plus, and then another tuple, sum, make sure it's a tuple, and then this just works. We just get a tuple with all three of these, because tuple addition, like list addition, is just going to concatenate things. So that's fine. But what I've got here is some error, and because I told JAX that this was a function that I wanted it to JIT. And so I'm basically asking it here to, first of all, treat this as static, and second of all, treat this as dynamic, and then do a computational graph where you replace the elements of this pie tree, what it looks like, where the leaf element is a built-in function sum, replace that with an abstract version. And it's basically going to say, well, I don't know how to replace a built-in function sum with an abstract version because it's not a JAX array. I can only do that for JAX arrays. Also can't do it for NumPy arrays or anything like that. So if we want to pass, I guess we should probably read the error. Let's see if this elucidates anything. So error interpreting argument to function, this is the function, as an abstract array. So like I said, it's trying to form some kind of abstract tracer from this argument. That's what it's saying. The problematic value is of type class built-in functional method. Now notice it is actually not complaining about the tuple containing sum, because tuples are fine as long as they're just pie trees. Tuples are fine as long as they contain at the leaf level of the pie tree JAX arrays. And so it's saying that this was passed to the function at the path A0. I'm actually not 100% sure what that means. Oh, no, yeah, that's clear. So A is the argument here, and this is a tuple, and A0 represents the first element of that tuple. So it's giving me the sort of pie tree address of this problematic argument. This typically, let's read on. This typically means that a JIT-wrapped function was called with a non-array argument, and this argument was not marked as static using the static argnums or static argnames parameters of JAX.JIT. That's quite a helpful error message. It's sort of told us exactly what we've done wrong, exactly where the problem was, in which function, and basically told us what we need to do about it. And that's what the takeaway from this is going to be. Notice that it was no problem passing in min and max for n. And if I if I call this again, this is actually not, no, that won't work because I can't make n static because, a static, because up here I'm using JAX arrays. But if, for example, I was able to pass this in as a static argument to a jitted version of f that expected a to be static, then this would work fine and I would get back this sequence of built-in functions. I mean, there would be no point. There wouldn't be an array computation, so there's no point using JAX. It's just going to build the computational graph that basically says, return as a constant this Python object. However, you could do that. So hopefully this helps us understand the sort of limitations of JIT with respect to static versus dynamic arguments. And now that we have finished up in the dojo, we're ready to try something a little bit more complicated if we go into HiJAX lesson, or I should say lecture 08. So what have we got here? We have BSGPT, which is my name for a byte-sized generative pre-trained transformer. So we're going to go in here and we're going to implement a byte transformer on the Sherlock Holmes canon, which is my favorite tiny text data set. And basically, we're not going to worry about any tokenization or anything like that. We're literally just going to train it on like ASCII characters. And so the vocab size for the transformer is going to be 128. Let's have a look at what we've got here. So we've got some imports. Nothing new here. Functools we're going to make good use of with our new pattern for applying static arguments to JAX, or configuring static argnames for JAX.JIT. We've got matthew.lib and so on for visualization and TQDM. We've got JAX typing, more of these types than we've used in previously, and notably we have uint8 imported as under the alias byte, because a lot of this is going to be a byte transformer, so the arrays that we're going to have are going to be arrays of uint8s, and so I just want to call those byte arrays basically. And then we have I can't remember why we have NumPy, but we have JAX and JAX NumPy and inops. We might not need NumPy, I can't remember. Okay, so yeah, what else have we got here? So there's a lot of code that's already been implemented here actually as a starting point, because it would take too long to implement the full transformer ourselves. We're going to go ahead and see what's here, and we're going to see how to accelerate it. So with JIT and supplying various static arguments. So the main is a normal main. We're going to load some data. We're going to configure the architecture, which we'll see we're going to need to implement one of these init parameters for the byte sequence model. We're going to need to initialize our optimizer, which is similar to what we've implemented in previous lectures. We're going to have a training loop. We've seen a million of these now. We've got like sampling a batch of sequences, and we're going to be computing loss and grads and doing an update. And this is This is going to be very similar to things we've shown in the past, but we're going to add an autoregressive completion visualization to this, and so we're going to need to compute some completions on some test data to make that work, and so we'll get to that in a moment. Then we have some helper functions for converting between strings and arrays of bytes. This will be super useful. We'll have a closer look at these in a moment. We've got a long amount of code on actually implementing the architecture, and we're going to need to take a close look at this to determine what is static, what needs to be static, and what doesn't need to be static. But basically, we've got a byte sequence model, which is made of an actual underlying decode transformer that operates over vectors. And then we have an affine transform that operates over. This is just the usual affine transform we've seen in previous that just operates on individual. It's just a linear transform with a bias. Linear transform, which is an affine transform without a bias. We've got layer norm, which is a sort of something that's used to stabilize the forward pass in the transformer in several places. We haven't seen this before, but you can take a close look at the code or look up, the relevant papers if you want to understand this concept. Decode transformer block. This is the individual sort of units that we're going to iterate in the forward pass of the transformer, and it comprises a attention computation and an MLP computation for some nonlinearity. We've got the initialization and the forward pass of that. The MLP is just a bunch of two affine transforms with a nonlinearity in between. The multi-headed causal self-attention is probably the most complex transformer or like module that we've implemented so far. And this is sort of based loosely on Andrej Karpathy's Nano GPT implementation, although it's got my own sort of twists on some of the ways of doing the code, and also it's written to work with JAX rather than PyTorch. And so I would actually recommend having a look through this code base if you want, and I may do a separate tutorial on coding up this transformer later. It would take like about 2 hours, I think, to code it up line by line and explain everything there. And so I'm not going to make it part of this tutorial. What we are going to do in this tutorial is go through and see how we can JIT things and what we need to mark as static. But this is useful to go through this because there's lots of examples of like slightly non-obvious uses of VMAP. For example, we use VMAP to actually compute the attention computation across heads. We VMAP across the heads, and that means that we basically have to only implement the attention for a single head at a time, which is much simpler. And so, for example, in the Nano GPT tutorial from Karpathy, there's a bunch of sort of messing around with dimensions of like a head dimension that's sort of bleeding through everything, whereas this, we just sort of get rid of that dimension and then add it in later with VMAP, and that makes things a little bit simpler to think about. So I'm pretty sure this implementation is sort of in good working order, although I haven't fully tested it. And we will see later. We might have to fix some issues, but I'm confident that we can fix anything that comes up because I have, I think this is close to a working implementation because I wrote it based on a working implementation that I had earlier. We weren't finished quite going through what's in the code. So after the transformer architecture, there's the sort of loss functions that we're pretty used to seeing. So cross entropy and then a batch cross entropy here that is defined to work over sequences in an autoregressive fashion. It would be cool to take a moment to look at this as well, but this is sort of like a language modeling thing rather than a JAX thing, so I'm going to sort of skip over the details right now. Then we have the optimizer that we've implemented previously, and the only difference here, I think, is that I've put the beta 1 and beta 2 in as optional parameters with the defaults from the Kumar and Barr paper, the Adam paper. And then there might be other slight differences in the implementation or the naming of variables because I rewrote it for this. And then we have some code for visualizing sequences of text, and we'll use this later to print things out. And that's the end of the file. So let's make a plan. Basically, we've just learned a little bit about static arguments, and we're going to now try to apply JIT to some practical deep neural network functions to see if we can understand what needs to be static and what doesn't need to be static. But before we do this, I guess we just sort of should start from the main and work our way through, and then as things come up, we'll want to sort of JIT them. So we're going to start by loading the actual data. And so to load the data, it's actually going to be very simple. Basically, what we would want to do is just open the data file. So with open, and we're going to go to our data folder, which is in the sort of parent folder, the root folder of the hijax repository. We have this data folder. And then in there we have this Sherlock file, sherlock.txt, which is just grabbed from Project Gutenberg as a plain text concatenated file of the entire works of Sir Arthur Conan Doyle on the character Sherlock. We're going to open that as a file. And then we can just basically grab this whole file as a string, data equals file.read, and that will just give us one big Python string representing the entire thing, all of the new lines, all of the spaces, all of the books, all in one big string. And so we could sort of just get a peek at how big this file is by going print length of data, or maybe we'll sort of say what this is. So num tokens in the training data, because remember our tokens are going to be bytes today. And we could just do the length of data. And then so that I'm not preempting anything, I'm just going to return prematurely from the main here. And so we can just get this output. And so if I run this, recall to run this on the TPU device, and then Python BS-GPT, I've CD'd into the lecture 8 folder now. I'm going to run this and see we get 3,867,381 tokens. So that is just under 4 megabytes of text. And this is not a lot of text to train a transformer on. And actually the transformer that we're going to train is going to have around 2 million parameters, 2.4 million parameters, and that is going to be like way too big for this. But we're not going to train it for that long, so it's not like it's going to overfit or anything. Yeah, that's that. But the thing is, this is a string. This is not really like JAX data yet. What we want is a sequence of tokens, and tokens we're going to represent as integers, uint8s, as I said, byte, and we're going to have a big byte array. And so we need a function to convert between. We need a function to convert basically from this string to an array of bytes. And one way to implement that, although there's maybe many ways to implement, is to use this approach where we can take a list comprehension through the string and use the ORD built in to get the corresponding code point, which is going to be a number between 0 and 127 for this data. Although in general it might be a larger integer. But for this data I've made sure that Sherlock.txt contains only ASCII characters, so this is going to be fine. And then that's a list, and then we're going to make this a JAX array. And we're going to make sure it's uint8 as the D type, so that we don't have some like int32 or something like that as the default if we were to put a bunch of integers in a list and then call JAX array. And so you might wonder, so yeah, as you can see here, this is a function that takes a string and returns a byte array of the length of the string. And so we can just go ahead and apply that. But you might be wondering, since we see this function here, should we go ahead and JIT it? And I think actually there's nothing stopping us from JITting it. No, maybe there is something stopping us from JITting it, and that is that this S is a string, and that's not something that we could treat as a JAX array. So we'd have to mark this as static. However, if we mark this as static, then the function actually has no dynamic parameters at all. And so what that would mean in practice is that every time we call this function with a different string, we're going to get we're going to miss in the compilation cache, and we're going to sort of trace the function. The computational graph is going to be like basically take this string, hard code it as a JAX array, and then return that JAX array. And we're going to then cache the string JAX array as the sort of result of that computational graph. And basically, then we want to try a different string, then we're going to need to compile it again. And so there's going to be actually no benefit at all from JITting this. In fact, it might even slow things down and use a whole bunch more memory that we don't need to use as the compilation cache kind of grows for this function. Even after we stop using certain strings. And so let's avoid JITting this. Now, while we're here, let's ask a similar question about this reverse transformation. So the array to string function is what we're going to use when we later want to take a sequence of tokens that we've built as a byte array, and we want to turn it into a string that we can print out onto the terminal. And so this is going to look sort of similar, but doing an inverse operation, where we take the array that is a byte array, and we go through it and we map it to each index in this array, which is an int uint8. We use the char built-in to figure out the corresponding character as a length 1 string, and then we use join to bring them together, and we get an overall string. So can we JIT this? You might like to have a think about it for a second. And the answer is going to be no, we can't JIT this actually at all, even if we mark things as static. And so we can't mark this as static because it's not hashable, it's a JAX array. And if we tried, that would be an issue. And if we don't mark it as static, then we're going to have a different issue. So if we don't mark it as static, we're going to be tracing this array, and we'll get to this point where we're iterating through, and this I that we go through will be like a tracer, abstract JAX JIT tracer of an int uint8, and we won't know what the value is, and then we'll pass it to this Python function chur, and it's not going to know what to do with that JIT tracer. It's probably going to throw us some kind of error. So we can't, we should just think of this as a Python function, basically. There's nothing we can JIT here. Actually, and there's no point in JITting this one, and so let's just leave these be. Let's go back up now to the byte corpus. And so we've loaded our byte corpus, and the next thing we want to do is configure the model architecture. And I should show you, so we want to run to here next. So I want to show you what this is doing. And note that in the main block here, configurable through the command line with Tyro, we've got a bunch of parameters here that are a little bit different than the ones we've had before. These ones actually control the size of the architecture. Previously, we've hard-coded the size of the architecture, like LaNet or a simple net was kind of like fixed shapes in all the layers, and we just had those hard-coded in. And even for our residual network that we were doing last time, for the residual network, we had a fixed number of layers that we hard-coded into the initialization of the residual network itself. Whereas here, we want this transformer to be basically configurable on the command line. And if you want to have a transformer that has even more blocks, like more than what the default here is 6, you can just change that on the command line. But what that means is that our initialization is going to depend on the value of these parameters that are coming from the command line. So we can't definitely know those at we will definitely need to mark those as static, because the computational graph is going to entirely depend on all of these parameters. And so in particular, we've got the number of blocks. That's the number of these transformer blocks, the number of heads within each attention computation, the size of the residual stream, the size of the sort of hidden dimension of the MLPs, the maximum context length, which is going to determine things about like the position encoding and how many sort of vectors we have to learn for the position encoding. The completion length is a little bit different. That's going to be in the autoregressive loop. I guess that's more of a visualization parameter, actually. But all of these ones are going to be, we're going to need to eventually mark these as static, because the size of the parameters is going to heavily depend on these. And you can see we're passing all of those into this model initialization function. And so this is an example of a function. When we JIT it, we're going to definitely need to mark some things as static. So let's go have a look at this byte sequence model init function, actually, and see if we can sort of get away with figuring out how to mark that as static. So what this is a byte sequence model has a single field, which is a decode transformer that operates over vectors. And this decode transformer is going to have internally a bunch of other modules, and eventually it's going to boil down to matrix multiplications, or sorry, matrices that we're going to put in the forward pass through matrix multiplications. Matrices for weights and bias vectors as well, I suppose. And there will be a couple of other things for the layer norms, for example, but it's still going to be eventually vectors. But the sizes are all going to depend on these parameters that come in the init. And so let's have a look at this init method and see we pass into the decode transformer all of these shapes. And so in order to do that, we're going to need to know, eventually decode transformer is going to need to know that they what they are. And let's just trace that through a little bit, shall we? So decode transformer, let's, for example, have a look at where max context length ends up. So max context length comes into the decode transformer's init method and gets passed into the position embedding as the number of inputs of a linear transform. So if we go to linear transform, then we can find that it has a weights, which has a num inputs num out array. And so the input here comes in as num inputs. That's going to be max context length, which is our sort of parameter that's come in. And that's going to determine the shape of a uniform initialization of a weights matrix. And so that is why we definitely are going to need to, on this init method of this thing, byte sequence model, we're going to need to mark that max context length as static. So let's go ahead and do our functools partial application to JIT this. Functools.partial, jax.jit, static argnames equals, and we can go ahead and put max context length in there. What about, I mean, the answer is going to be the same for all of these basically, but we should just sort of see it through. So embed size. So embed size, oops, let me spell that right. Embed size, where does that show up? So it also gets passed to the decode transformer as embed size, and then the init method of the decode transformer is going to take that embed size and use it as the num outputs of a linear transform. Okay, so we already saw that that was going to be required later, so we better also pass that in as static. And basically we could go through, and you might like to take a close look at the, while you're taking a close look later at this transformer implementation using the GitHub repository, you might like to take a look through and see where the MLP size, the num heads, and the num blocks shows up. The num heads is a little bit special actually. Let's do that one, but let's just type these now and I think this is going to work. So MLP size, num heads, and num blocks. Now the num heads is special, num heads, because when that shows up, it's showing up in the init method of what's this, the decode transformer block, and then it's going to get passed into the init method of the multi-headed causal self-attention, which is really like the heart of the transformer, I suppose. And here we are. So I've kind of given the game away with the code already here, but let's have a close look at this multi-headed causal self-attention. Num heads shows up as a part of the class itself, not as a part of a shape of a matrix. However, if we have a close look in the forward pass, we can see that we do require num heads to be part of a shape because we're doing a rearrange. And this is, we're basically going to like do a bunch of transformations on the queries and keys, on the query and key activations and value activations. And then we want to split these up by head. We want to sort of do them all in one batch and then chunk them up. And then we see here that we do this with inops, and this is eventually going to require making a matrix of a shape 3 for the different sort of matrices, and then T for time as in the sequence position, and then num heads here and head size is going to be part of the shape. So there is eventually going to be a matrix that depends on the shape. However, this is sort of actually coming from self num heads, not the input num heads. But that input num heads was going into the multi-headed causal self-attention in the init method. So if we keep looking, we will find this num heads come up in the init method, and it ends up being attached to the multi-headed causal self-attention thing. And so in principle, there's actually nothing wrong with attaching a JAX tracer, a JIT tracer abstract thing to this multi-headed causal self-attention as a leaf. And then it could depend on what this value is, and we could compute the result of this initialization without making num heads static. However, then when we come to do the forward pass, we'd have this problem that we would be depending on an abstract value that is coming from self. And self here is going to be the instance of the multi-headed causal self-attention, and that is going to have this leaf somewhere that is going to be instantiated when we JIT this as a abstract array. And then we're going to try and use it for the shape, and we're going to run into this issue when we use self-num heads. And so the way around this is both to initialize as static well, let me say first, in order to get this self thing to work, we've faced this problem before actually, and we had to use the meta fields key of the register data class function. And as we're registering the data class, we needed to note that this field is not a value field. It's not a leaf. It's not part of the structure of the pie tree as a node. It is part of the structure of the pie tree in an analogy to a shape of an array. It's part of like the shape of the pie tree, or something. I guess the structure actually is the right word for it, but it's not part of the data of the leaves of the pie tree. And so we've sort of distinguished here between these different transforms. We've got the QKV and the output transforms, which are just normal parameter. Well, in this case, modules. They'll be sort of further nested inside pie trees, but eventually there'll be parameter matrices here, or parameter arrays. And then this num heads, we've said that one's a meta field. And so that means that when we create this multi-headed causal self-attention, part of the structure or like shape of the pie tree is going to be this num heads. And that is going to make the forward pass work. But what that means is that if we go back up to the byte transformer and we're passing in num heads here, then when we eventually pass in num heads in the block to initialize the multi-headed causal self-attention, we're not going to be able to instantiate a multi-headed causal self-attention module unless we know this value concretely, because it's needed to determine the shape of the pie tree, because it's needed to determine one of the meta fields of this pie tree. And so we still need to mark this as static, in the initial init method. And that is what we have done now. So we've marked all of these as static, but that one numHeads was a little bit special, and sometimes you'll face that kind of thing. I should note that another option would be later in this. Another option would be to take this. Where is the multi-headed causal self-attention? I guess it's one of the last blocks that I defined, so it's all the way down here. Another option would be to. Here we are. Another option would be to sort of say, well, this self method, maybe we could just mark that as static. But that would be an issue because actually we can't mark it as static because these things are in there and these contain JAX arrays. And we know that we can't mark JAX arrays as static. We'll have an issue where they're not hashable. And so the only other option then would be to sort of split up this pie tree into two different arguments, one that contains all of the meta information, and then we can mark that as static, and one that contains all of the data, and then we can mark that as dynamic or not mark it as static. And then we'd have two different arguments in this forward pass. But that can be quite inconvenient, and sometimes it's quite natural to pair these sort of these numerical shape information as the fields of our modules. And you could sort of have a similar thing with many other modules that you could have. Like, for example, one thing we could have done is we could have taken this affine transform and linear transform and had a field that said whether or not to use biases at all. And it could be a Boolean field. But then that's going to determine the computational graph, whether we add biases or not. And so that is going to need to be sort of marked as a meta field. And it would be a little bit awkward to have sort of different versions of the module, or that is how we've implemented it here under different names. It would be certainly annoying to have to define in the forward pass that you pass in a self and you also pass in some configuration object that you have to track around and sort of keep with you at all times and sort of keep it separate and in parallel. So this is going to be the approach. Now we've successfully then jittered the byte sequence model's initialization. What about the forward pass? So the forward pass here, it doesn't look like anything is going to depend on the values of these things. So the leaves of the pie tree that corresponds to this byte sequence model itself is just a decode transformer, which boils down eventually to a bunch of layer norms and linear transformations, although composed in interesting ways that make sort of attention happen and make the magic of the transformer. But these are all arrays, apart from this numHeads field, which we sort of already handled at that point down below. And then we should also be able to sort of think of this byte array as just data, and so we can JIT over that no problem. Nothing depends on the contents of the byte array for determining the course of the computation. It does depend on the length, but that's already part of the shape. And so that is already statically available. And so we're going to see later that when we take forward passes, we're going to need to recompile every time we want to take a forward pass with a different length string, which is quite relevant for autoregressive language modeling. Okay, so we'll just JAX.JIT this with no need to mark anything as static, and I think this should work, and we should actually be able to get at least the initialization going now. And so I'm going to see if this runs, this init, and then see if we can count the number of parameters. And then we're going to see if we can get the forward pass to run after that. So let's start by seeing if we can, if we've done enough to JIT the init method. And it looks like we have. So we configure the model architecture. It's obviously traced it and compiled the initialization, and then we've actually executed and got this pie tree back, and we've walked through the pie tree. We've sort of iterated through the pie tree's leaves, and we've taken the size of each of them, and we end up with 2.45 million parameters, so 2,451,072 in total. And just to sort of check, if we sort of said we want the num blocks now suddenly to be 12 instead of 6, then we would be able to do this again, but it would give us a different number of parameters, 4.8 million this time instead. And so basically double, so that makes sense. It's not exactly double because there's sort of things that aren't blocks that are like a constant offset. Okay, anyway, so I think we're ready to move on now to talking about this forward pass. So what I've got here is testing model completion. And so I think we're going to get to that. We're going to do some like autoregressive completion. But first, let's just test the actual forward pass itself. So what this forward pass took, it looks like, was, if we have another look at this, the forward pass took, sorry, I've gone too far. The forward pass took as input a byte sequence model itself, so it's just like a method on that, and then it takes a byte array, which is going to be an array of bytes of length t. And we have this max context length in mind of 64, we've sort of parameterized it as. So maybe we can just grab 64 tokens from our data set and put them into the model and see what it spits out. And so let's try that. So let's just say maybe like t's equals, actually, you know what, I'm going to come up with an actual prompt that might be interesting. And so what I would like to do is use the prompt, I would like to use the prompt as a string right now, space Sherlock Holmes and Dr. W. And this is how long? So this is according to Vim 30 characters long, and so that's well within the max context length of 64 that we've configured. Let me just double check that it is 64. Completion length, max context length, yes, 64. So this is well within the 64 completion length, and so this should be fine. However, currently it's a string, not a byte array, so we can take this, and I want to keep this prompt around, so I'm going to call it the original prompt, because later we're going to be sort of appending things autoregressively to a prompt. And I want to take the actual tokens of the prompt and say that's going to be stir to tokens of prompt. And then I can like print this out just so we can get a look at it. Original prompt tokens. And there's nothing we can JIT here, but it's very simple, so it should run fast anyway. I have to make sure to remember to go down back to 6 blocks. Stir to tokens is not a right. What did I call it? Stir to, it's here. Stir to. Oh, I didn't actually remember to implement this. So to fix this. So first of all, we're going to need the data to be stirred to. What did I actually call it? Stir to. Stir to array. Okay, yeah, we just got to call it stir to array instead of stir to tokens. And we're also going to need to stir to array this, by the way. I forgot about that, sorry. So make sure our data for training is going to be like JAX arrays. But anyway, now we've got stir to array, and I'll get rid of this numblocks 12 and just use the default 6 block architecture. Loading the data, and then configuring the model, and then, okay, we have an issue. Original prom token, okay, it's just a typo. Prompt tokens. It should be prompt tokens. I'm really not doing good with the spelling today. Sorry. Here we go. Okay, so 3232. We know 32 is well known to be the ASCII code for space, and then so on. Sherlock Holmes and Dr. Watson. Very good. Or Dr. W, I should say. So space W, and then we're going to see what comes next. We'll let the transformer decide if it wants to predict that ATSON comes next. Okay, now we're going to need to, so we've seen the forward pass, and it looks like it's jitting fine. Now what we need is a way to sort of predict a next token using the actual forward pass. Oh, we haven't actually done the forward pass. I just printed out this. That's right. Sorry, we're getting a little bit ahead of myself. So we've got an input, but we need to get an output. So let's take our model dot forward and pass it on original prompt tokens and see what we get. So let's say this is like next token probs. Actually, I guess it will be next tokens probs, because the way the transformer works is actually that it outputs a prediction for all prefixes. And so let's just show this. Next tokens probs. Let's show the shape of this, and let's see if we can figure out why it is what it is when we do this. Okay, so now there's an issue. So this has got to be something to do with, this is something that we have to figure out. Yeah, okay, this is, sorry, coming from deep within the transformer architecture. So I'm going to pause the recording and then figure this out and then come back. Okay, so yeah, I fixed the issue, actually, and then a couple of other issues that were just typos when I typed out this transformer implementation, but it's now working. So let me just run this again. What we were hoping was that we were going to get the next tokens probabilities and see the shape and then try and figure out what this shape means. So what this shape means is what the shape is 30 by 128. So let's see if we can figure that out. And so we noted that the prompt itself was 30 characters long, which means this byte array that we get is going to be of length 30 as well. It's going to be sort of a single dimensional JAX array of length 30, size 30 in the one dimension. We're going to pass that in, and the model forward, the forward pass says that it should give us back a t by 128, where 128 is the number of ASCII characters. This is the vocab size. And these are represented as probabilities of the next character being one of different things. So what this means is that after you've seen each prefix of the 30 prefixes that we have in this transformer, we're going to interpret this to mean what is the probability that the next token that you would see is going to be one or another thing. And so, for example, I could have a look at one of these. I could have a look at just one of these and maybe the last one. Yeah, so let's have a look at just the last one of these. So the one that corresponds to predicting what comes after the full sequence of 30 characters. Yeah, that's right. The thing that is going to come after that is going to be given by next tokens probs, and then we'll index into the -1 position in this 30 array, and then we're going to get a 128 vector. So I can actually print this vector out. It's just going to be a floating point vector, and I'll see how it looks when we print it out. Configuring the model architecture again. Here we go. So we've got a bunch of numbers between sort of like their probabilities, and they're all like pretty small. Some of them are larger than others. But of course, this is a randomly initialized transformer, so we shouldn't look for too much structure here. I would say that on average, with initialization, this is going to be like a roughly uniform distribution. And it's certainly not going to have any luck predicting things. For example, like I don't know what the highest thing here is, but it ascribes more probability than I would that we're going to end with that we're going to have a null character next, a sort of 0 ID, and also some of the higher ASCII bits that they're sort of less. These like ASCII characters down here are sort of indicating things that don't turn up in text too often because they're like control codes and things like that. And so when we train the model, we're going to see what kind of tokens it predicts, and we're going to see that it very quickly learns to predict things that are more likely to be like spaces and letters and maybe even numbers sometimes and punctuation, and not so much these sort of early sort of symbolic or like meta symbols that are in the early stages of the ASCII character set. Okay, so this is pretty cool. We've sort of tested our forward pass. And I'm just going to comment this out now so that we have slightly cleaner output going forward. And we would like to actually test this autoregressively and sort of see, it's going to sort of output gibberish right now, but let's see what it does output. And then we'll be able to have a visualization of the kind of output that our transformer gives, and when we train it, we'll be able to see that sort of gradually improve over time in the way that I'm claiming we will see. So let me just see what we need to do to figure out how to autoregressively generate. And so instead of talking about, we will keep this original prompt tokens, but let's define a new method on the transformer class that's going to require, I think it makes sense for it to be on the transformer class because this completion logic is going to be a little bit intricate. So model.complete is going to be a new method. We had model.forward, we're going to have model.complete, and it's going to take a key. The reason why we would want to take a key is because we might want to do some sampling with some temperature of this sort of probability distribution represented here, rather than, for example, taking the maximum likelihood token. The token that it predicts them is the most probable. We might like to sometimes take a less probable token. So we're going to need a key to sort of do that random sampling. And so I better key completion key equals jax.random .split of my ongoing key. And so I'll pass in key completion here. And then let's see. So we're going to want to pass in the prompt tokens that we want to use. And so we want to prompt in these original prompt tokens in this case. And then what else? I guess we want to say how many tokens we want out. So we have this completion length argument coming from Tyro. Let's use that. So num tokens out a equals completion length. And then this method hasn't been implemented. So our job now is going to be to actually implement this model.complete method. So let's go down to our byte sequence model and say we want to add a new method. So we have the forward pass, we have the initialization. Let's add a new method somewhere here in the middle that is going to be, we're going to hopefully be able to JAX.JIT it, but I think it will be a little bit trickier than other methods, so we'll see how we go. We're going to start with not JITting it and just call it complete. And let's see what we want the inputs and outputs to be. So I guess we should have self in here because it's a method. And then I already said what the inputs should be. We should have a prompt tokens, which is going to be a byte array. And that could be of sort of any length. I guess I got to do this right. Byte, and then subscript array, and then the shape can be some like initial length. And then I want to have a, what did we call it? Num tokens out, which can be an int. That's probably going to need to be static if we were JITting this, because it's going to determine the shape of the output. So the output is going to be another byte array. And that byte array is, I gotta do this right. So byte and then square bracket array. And then this is gonna be t plus num tokens out, I believe, is what we'd be aiming for. Or maybe we'll just do the num tokens out, and we can append it later to the, we can append it later ourselves. The caller can append it if they want to do autoregressive generation. This would just be sort of the answer that the sequence model gives to like a question that we ask it or something like that. Let's go about actually implementing this. And to do that, I just need to remind myself what's involved. Okay, yeah, this is a little bit tricky. So this is going to take us. Another thing that I had as an optional parameter here in my code that we might as well have is inverse temperature, which is a float. And I'm going to set it to a default value of 1. And I think basically we should not worry too much about this. If you like, you could add it to Tyro and then configure it in the calling code. But we'll just write the forward pass, the completion logic so that it's doing the sampling with this temperature. And then that is in principle configurable, but we're not going to play with that today. So let's just see if we have num tokens out. It would be nice probably to know how many tokens we had in. And that is just going to be equal to the prompt tokens.shape. Now, if we were JITting this, this should be fine. We shouldn't need things to be static to know this integer, because this is, even when this is an abstract tracer array, we're going to still have the shape known by the tracer array. So this is just going to be an integer. This is fine, not abstract. So the approach we're going to use here is to have like a buffer that we're going to use, and we're going to do some sort of slicing around that buffer to create prompts. And then when we get new tokens out, we're going to add them to the buffer and move a sliding window along it. Because we have this max context length to worry about, we'll also have to slide the end of the window to keep up with us. So we're only ever passing max context length into the transformer at once. And we're going to do just a very simple approach where if anything is beyond the max context length to go, we're just going to discard it from the next forward pass. But basically, we're going to be sort of setting up this buffer and then going in a loop and generating until we fill up the buffer with the number of tokens out added from what we started. So let's start with initializing that buffer, or I guess I should say initialize buffer. We should set up that buffer with jnp.concatenate of the I guess concatenate takes a list of things, so we need to sort of give it a list of the prompt tokens, and I guess we want like a blank section, so I might as well just fill this with zeros, jnp.zeros, as long as I make sure it has the right shape and type. So num tokens out is going to be the number that we need, and we want the d type to be uint8, which is our byte type. jnp.uint8. Now this should give us a buffer that is filled. The first num in positions in the buffer have the prompt, and the rest is blank, and we're going to need to sort of one at a time put an actual value, an actual ID of a token in there, and then slide a window across and keep passing in the last 64 things to the transformer. So let us now do that for loop. So we're going to loop now this is going to be tricky to keep in mind in terms of one thing I forgot in the input actually, which we need now, is the key. So key is a PRNG key array. Sorry about that, added it now. Okay, so let's loop across the buffer. We're going to need to have a key that we use whenever we want to take a random sort of thing. And one thing I want to do is I want to do this in a way so that if I was to call with a given key and call the call for a certain number of tokens and then come in later and call for a different number of tokens, I should get the same first prefix of the tokens. The sort of common prefix should be the same if I'm using the same key. And so I think the best way to do that is going to be inside the loop, forking the key as we go. And then if I would sort of build part of this prefix, and then if I would call this again with the same key, I would build like a longer prefix. I would build that prefix and then I would keep building. So that's sort of the default way to do it. So that should be fine. I guess what we need to actually loop through then is just the indices of what we want to add to this buffer. And so we want to have basically for I in range num tokens out, and the and we need to now get a window that sort of ends before this position and has up to 64 things. And then we want to put this window into the transformer, and then we want to get the sort of output of the transformer, which is going to be one of these probability distributions. And then we want to sample that probability distribution with some temperature, and then we want to put that into the position I. That's what the inside of this loop is going to do. Okay, so let's do that. Let's prepare the slice. And so I guess we're going to go from some lower bound, which is going to be sometimes we might have like less than 64 tokens in the prompt. So I can't just do, for example, I minus 64 or like max token length. In fact, where am I going to get max token length? That is interesting. Let's think about that for a second. What I basically am going to need to do is something like max context length, I should say. I'm going to need to do max context length, and then I'm going to need to bottom this out at 0. So I need to make sure I do like max of 0 and this. And then, oh, actually, you know what? Also, this is wrong because we should start from the num tokens in plus I. And so what I'm getting a little bit confused. Maybe I should draw a diagram. That will help. So, so we have this idea of we have maybe like some prompt part of the array, and then some part that is to be filled up. And this position here is num tokens in, and I is going to go through 0 and then 1 and then so on. This is going to be I. And so if we keep this in mind, this should help us to figure out what the window we need to be. So the window we need to go potentially back 64 characters or max context length from num in plus I, which is where we're up to sort of next, but we also have to worry about the case where that would take us further than the end, and then we're going to have to do something about that. And so this should be the sort of lower bound. I think I've got the formula right here. So if we take num tokens in, that's the initial position, plus I, that's the current position, and then minus max context length, that takes us back to the start of the window. And then maxing that with 0 will mean that we'll only keep it if it's positive, and if it goes negative, we'll just go all the way back to 0. And then what about high? Well, I guess high is just going to be num tokens in plus I, which is going to be by design sort of the position that we are about to fill. And if we use this as an upper bound of a slice, it's not going to include that, which is exactly what we want. And you can sort of just see that the max context length, this is going to be up to max context length in length from low to high. So I think that should do it. And so we can now grab the window, which is going to be a slice of the buffer. And it's going to be a slice from low to high. Okay, that should do it. Although this, I'm going to flag, is going to be hard to JIT. So we will have to, because this is going to be a slice that depends on some parameters that aren't going to be static, because they're going to be sort of like a loop variable, unless we want to unroll this basically. So at least it will be hard to accelerate this loop. It might be actually not so bad to JIT if we were to unroll it. But anyway, let us move on. So the next thing we need to do is take this window and like actually predict a next token. So let's predict next token here. Okay, so in order to predict the next token, we've kind of already done this once, where we sort of got this distribution. We just need to do this again and then actually sample from the distribution and then use a temperature parameter. So let's do that. How we got this was we put a token sequence into the transformer. So we've got this model, which is self, I should say. Self.forward, I guess is what we're going to want to do. Self.forward on the window will give us something like this, which will, no, the window is something like this, and it will give us something like we saw before of like the 30 times 128 array. And we're going to want to go into, that at the final position and get, that's the probability distributions for the next token. Prob next token is this, or I guess I should say prob's next token. That's the probabilities for the next token. And so then we should be able to turn this into an actual next token using some randomness. So this is where I guess we're going to need to key, we're going to need to split the key and go key generate, and then key, which we've passed in, is going to be jax.random.split of key. And then next token, we can use JAX random choice for this. We can use JAX random choice, and JAX random choice allows us to pass in obviously a key. This would be the key generate. And then we are allowed to pass in a range, the array or integer that we want to pass in. We'll pass in a range, and this will now give us an ID between 0 and 127, if I put this as 128. And then I want to I want to use a particular probability distribution of prob's next token. And then I want to make sure that I raise this to the power of the inverse temperature. So let's just double check that this is the right way to do it. So what this will mean is, okay, first of all, this will no longer be a normalized probability distribution, but it will have the property that, or random choice has a property that it normalizes the probabilities that you give it anyway, so we don't need to worry about normalizing this. And let's just check that it works. If I put in an inverse temperature of 0, so a temperature of infinity, that should correspond to fully random generation. So a temperature of infinity means that like it's a very high energy system and things are bouncing around all over the place intuitively in physics. And in this, in the context of probability and statistics, then also a high temperature corresponds to fully randomness, a uniform distribution over tokens. Well, if I put inverse temperature as 0, then this raising these things to the power of 0 is going to set them all to 1, and so that's going to do exactly what we want. And likewise, if I set this to very high power, then the differences here are going to compound. We have a high inverse temperature. The probabilities are going to become much more sharply concentrated once we normalize them around the things that are the highest. And that will be like having a very low temperature. So high inverse temperature, low temperature. That would be like a very low energy system where it's kind of likely to be in the lowest energy state. And that is analogous to sampling the highest probability token. Okay, so that seems like that is right. And then we just, I think this is the default, but we maybe should put in a shape to say that we only want one choice from this and we want it to just be a single scalar. And so we get this next token, which will be an integer, and we're ready to sort of append that to our buffer, or like, I guess, assign it to our buffer. And so let's do that next. So add the chosen token to the buffer, and we can't mutate the buffer because this is JAX, but we've done this a few times now. We just need to use buffer.at, and I guess we're at num tokens in plus I is where we want to make our insertion, remembering that when I is 0, for example, we want to insert here, and num tokens in, which is sort of the position corresponding to the length of this with zero-based indexing, and so on. If we have generated so many tokens so far, we want to insert at the next position, and we want to set this to next token, not next token. And I think that is actually all. If we make it through this loop, we will have filled in num tokens out, which is the size of the blank section of the buffer. And the last one of those will be num tokens in plus num tokens out minus 1, which is also the end of this array of length num tokens in plus num tokens out. So that checks out. And I think we're free of off by 1 errors, therefore. And so let us now return the completion. I guess we're basically done. So to get the completion, we just need to make sure that we take this part of the buffer that corresponded to this and not the original part of the buffer. And so we can just return the buffer and then do a slice to get the negative num tokens out and everything from there onwards. So this will be the last num tokens out parts of the slice, and that is exactly what we want to return. So that's great. That is, I guess I could make this a little bit more verbose by saying this is, we want to return the completion, and we want to say tokens out, because we had prompts tokens. I guess I could have called this tokens in, or completion tokens maybe, and then return tokens out. And that is this completion. So we should be able to do some completion now, and then that means we should be able to visualize some completion now. But I'm going to start by seeing what we need to do to actually visualize. So we've got our visualization code down at the bottom of the script that I flashed up earlier. Let us see what model complete will give us. So it'll give us our tokens out. So we'll call this the completion, or completion tokens. Equals model.complete, and we've just implemented this now. Oh yeah, we haven't figured out the max context length thing. That's still an undefined thing. We'll come back for that in a second, I guess. Now that I'm up here, I just want to print viz, if I just call this viz example. So this is to visualize a single piece of text. We give it the prompt. It takes strings, so we want to give it the prompt, which was a string here. And then we want to give it completion equals completion tokens, but we'll use our inverse of stir to array to stir of the completion tokens. And then I think it also takes some parameters that correspond to like progress in the training loop. So I'm just going to fill those in with different default values for now. Num steps, sorry. So we'll set lowercase t to maybe -1, and then, 0, and then capital T to num steps. That's going to be sort of useless progress indicator now. And so before we run this, I do need to figure out that max context length issue. So let me just max context length for the completion code. Where is this going to come from? Okay, so I think this might be a situation where we need to put this as either another field here and then put it as a static field, but it's a little bit annoying. And if there was some way to tell it from the shape that is already known statically, that would be nice. So the solution that I found to do this when I did this earlier is that we can make this a property. And then it's sort of nice that we don't have to keep marking it as static all the time, but we still have access to it later. So what I'm going to do is make a property and make it so that I can basically just say this is self.max context length, but without adding that actually to the pie tree and then having to specify it as a meta field. So self.max context length, and this is going to work because I'm going to be able to set a property of def max context length, and this will take self and return an int because max context length is an int. And then how we're going to get this? Well, I'm going to delegate to getting it from the underlying decode transformer, where this is actually stored in the shapes of the parameters of that. So I'm going to do this. I'm going to say this is return self.decode transformer dot max context length, because that also has a max context length in the initialization, so it makes sense to sort of assume that it would be able to return that as part of the API for the decode transformer. So let's go to the decode transformer and see about that. So it clearly doesn't have a max context length key in or field, and we would also have the same problem here, but remember we put the max context length as the num inputs for the linear transform, so I should be able to get it from that shape. And so I'm going to add another property here that goes looking for the input size of the token embedding, or was it the position embedding? Let me just double check that. I think it was the position embedding. Position embedding, linear transform, max context length is the num inputs. So I'm going to come back up here and add a property that says a decode transformer, just add it to the API, will expose a property which is called max context length, and that takes self and returns an int again, and that is return self.poston embedding dot, I could do the same thing. I could say num inputs, and I could just assume that that is part of the API of the position embedding, which is a linear transform. So let me go now to the linear, let me go to class linear transform and say, okay, you are now going to have a property, def num inputs, that obviously has to take self as an argument and return an int, and then is going to return. Now I can stop. So I can say self.weights dot shape 0. And that is because this weights is a float array, and even when it's a tracer, it has a shape, and the shape is n in, n out, and so n in is the 0th component of the shape, and that is going to be the number that we need. Now, if you liked, you could go through all of these modules that you define, and you could sort of have these intuitive properties that you can use for programming. And if I was writing a modular neural network library in JAX for general use, I would probably do that. I would probably add this feature so that you could sort of easily access the shapes of the components without knowing about the internal implementation, to have proper encapsulation of things, and that would be really nice. But at the moment, this is what I need for my immediate use case. So this is all of the properties that I'm going to add, and I don't want to sort of take the time to implement the others. But now I actually think this should work if we can make sure that we don't have any syntax errors or other typos. So I've just missed one bracket here, one closing parenthesis, and then hopefully, okay, there's no more syntax errors, but it remains to be seen whether there are other errors. Okay, key generate, it was an issue. I must have had a typo. Generate, I actually called it when I was splitting. So key gen arrayed. Well, I made it pretty far into the code, so hopefully there's no more issues, but I guess we'll see. This doesn't look nice. So first thing to notice is this is taking a while. We haven't jittered, that's probably why, the completion. And then we're getting these warnings, and I haven't seen that before, so I better have a close look at where that is coming from. But I think eventually, after we generate like 512 of these things, we should get a visualization of the output. So I think every time it was going through the sort of loop, it was probably generating one of these warnings. And I think this is easily fixable, actually. So this is a bit of a cryptic error, but scatter inputs have incompatible types, cannot safely cast values from dtype int32 to dtype uint8. And so I think that I need to like put a cast somewhere in the completion code where or complete it was called, where I have assumed something would be an uint8, and it's probably when I'm setting this next token. So I might have to go to this random choice maybe and say I want to make sure that the dtype. How did I solve this problem in my solution? Perhaps I didn't. Perhaps this only came up Oh, yeah, no, I did. I just forgot to put something. So I need to take this thing and I need to actually cast it. So as type is how we will do a cast in JAX. And I'll say the new D type of this thing should be jnp.uint8. And I simply forgot to add that compared to my solution that I had working earlier. And so that should get rid of this warning. And thanks, JAX, for telling us that it's unsafe to sort of say that if you have all you know about this thing is that it's coming out of this random choice that returns generally integers if you give it an integer, and it's an int32. And it might be that it was like overflowing or something like that when I was treating it as an int32 when I was setting it into this array. And so that's nice of you, but I didn't need it, and because it actually is safe because it's definitely between 0 and 127 inclusive. And so now I should be able to run this again, and it might go a little bit faster, hopefully, without sort of triggering this warning a bunch. It hasn't taken that long when I've been testing previously. It's taking a while, maybe a little bit longer than I thought. But there's a lot going on here. So actually, let's just have a think about what is going on here with our knowledge of static variables and compilation caches. So this model.forward is jittered. And so we actually should be going through this fast. But the thing is, we're calling it with increasing size windows repeatedly, right? And so every time we increase the size of the window, that is changing the shape of the input t to the model forward, and it's going to trigger a retrace and a recompilation. And so that is probably what's going to cause this to take so long the first time. But if we called for a second completion, it would probably be faster. And eventually, by the way, once we get going, because we're generating a bunch of tokens, we're going to hit the point where the buffer is of a fixed size, and then we should be at that point generating quite consistently using the one sort of version of this function in the compilation that will already be in the compilation cache. And so the first 34 of these, before we hit the max context length of 30 plus of 34 equals 64, will be triggering recompilations because we'll be first calling with a buffer of size 30, and then 31, and then 32, and then 34, 33, and then 34, and so on. And then eventually when we get to 64, the next one, we're going to slice off the first token that we were generating. And so then we're going to be calling repeatedly with 64, 64, 64, 64. And that should then be able to reuse this. However, we're still doing a lot of this tracing and key lookups and so on. And it would be nice if we could JIT this whole thing. And that is going to be a little bit trickier. Let us come back to that. I just want to implement the actual forward pass of the model first. Not the forward pass, sorry, the training loop of the model, and then get it actually training. Because what we can see right now is that even if we sped up this generation, it's just outputting nonsense characters. So you can see here we have Sherlock Holmes and Dr. W was our input prompt with the two spaces at the start. And then it's sort of printed out what the model has decided to say next. And it doesn't look like human readable or human text at all, really. It's just a bunch of special characters. Every time you see /x14, that is representing a hex code for digit 14, which you have to then interpret as a hex number, and that is not a printable character, so it prints this instead. And for example, here's another one, 7f. And these are non-printable characters which don't really occur in the data set, so it shouldn't be predicting these with any probability. But of course, it's just randomly initialized, so we have to actually train it. And so that is the next step. And so once we've got this visualization example working, I think we're ready to move on to that next step. So let me just move along to this training loop. And actually, the training loop is written, and there's not that much that is sort of different about this than the kind of training loops we've written in the past. But it's like slightly different in that when we choose the batch IDs, we're choosing like positions in the data, and we can't choose anything that is like too close to the end, because then there wouldn't be like 64 characters to take and put into the actual thing. So we are just have that special sort of quirk, and then we also have this idea of adding this. We're doing this with the batch size 1, and then we're taking this A range to represent, like, we want contiguous sequences of tokens starting at these randomly chosen positions, not too close, and then we want to broadcast addition with this A range so that we get basically a big array of sequences And this is just one way to sample sort of subsequences from the text data. And so that this data batch will have the shape of batch size times t times 128 representing the actual tokens. That's a little bit tricky, but also like language modeling thing rather than exactly a JAX thing, although I guess it's a little bit interesting to see how that's done using JAX. But anyway, then this is very standard. So we're just value at gradding the loss function, value and gradding transforming the loss function, and then getting the train loss and the grads. And then we are using our optimizer, our Atom optimizer, to get the updated op state and the model delta, and then we're using JAX tree map. We've seen this a few times now. So what we want to do now is sort of add this completion code to the loop. And this is a little bit of visualization code. And I think it's going to give us a bit of a fun visualization. So I want to add this and then talk through what it's doing. And then we'll be able to see the model training, learning, and getting better and better completions as it goes. So let's do that. And we're going to need a completion key. So let me just change this from to do to actually doing. So we're going to need a completion key for the completions. And we'll just fork that off the batch key, or the standard key, jax.random.split of this key. And then we're going to need to actually do the completion. So completion tokens equals. Now, what I want to do is actually, it takes a while to do the completion. This would slow us down if we did this every step. So what I thought of is instead, we'll do a fractional completion every step. And then every time we fill up our full completion length, we'll go back to the start and we'll generate maybe 8 tokens at a time from any given model, but then we'll generate 8 tokens and we'll add that to the prompt. And then we will take a training step and then we'll generate another 8 tokens and so on. So let's do that. So that would be model.complete with this key equals the completion ID. And then we can also pass in the prompt tokens equals, well, okay, we could pass in the original prompt tokens, but what I want to do actually is have a running tally, which I'm just going to call now prompt tokens. And when I generate my 8 bytes, I want to add that to this prompt tokens and then use that in the next training step, so that each training step we can be sort of growing the same prompt. And so let's initially set that to original prompt tokens, and we'll keep resetting it to original prompt tokens every now and then, because otherwise this is going to go nowhere. So let's take the prompt tokens to be these prompt tokens, which are going to kind of grow throughout this loop. And then the completion, so the num tokens out, sorry, we said we wanted to grab just 8 tokens or something like that. What we'll do in general is we'll do completion length divided by the num steps per reset, which is another. These are parameters that we had from the main function coming through Tyro through the command line, so we can configure this later. But num steps per reset, because every time we hit that many steps, we're going to go back to the start. So I want to make it so that by the time we've done that many steps, we've gotten the sort of total completion length that we had in mind. Okay, and so then that should be the completion. That will give us some new tokens. And then I guess I want to now plot what we've got. So we'll generate this plot and we'll call it viz example. And this is just like we just did before. But instead of printing all of the characters at once, we're just going to print everything we've got so far. So the prompt will be array to stir of the kind of running prompt tokens that we've got. And then the completion will be the array to stir of the new completion tokens that we just got out. And then the t, now we can actually put in the step. It will tell us how far through training we are. That will come up here. And then the total number of steps is this capital T num steps. That's going to tell us how far there is to go. So this is a bit of like a mini progress bar. Num steps. So that will be our plot. I guess we should print this plot, but before we do, I want to talk about updating the tokens as well. I guess I could do this here, but I wanted to do it before I passed these in because I want this to snapshot the sort of state that we were at. Actually, I guess I can do this way. So I could print this now and actually complete the logic of showing this. So what we want to do there is initially we want to just print this plot, but then usually we're going to want to override the previous plot. But when we reset the plot, then I want to have the old one stay above. So I'm going to not reset. I'm going to, every time I'm sort of generating from the initial prompt, from the original prompt, I want to not do the reset trick. So the way that's going to look is if step is, if step modulo num steps per reset. So for example, this is true for the first step, step 0. If that is equal to, if that is equal to 0, that's true for the first step, and then every time we've hit our like num steps per reset, that's going to be true again. And in that case, I want to print the stir of the plot. I want to print the plot, but I'm using TQDM actually for this training loop, which we haven't seen yet. But when you're using TQDM, you have to use TQDM write instead of print, and then you have to give it a string rather than an arbitrary object that it converts to a string. Not prompt, I want plot. So I'm going to do it like this. And then in all of the other cases, I want to also print out a string. This will print it above the progress bar, by the way. But I want to do my trick where I print the negative of the plot, and then the plot, and then that will sort of scrub before I print the plot. That should work. So this code here basically prints the plot, and now I want to make sure that I'm tracking my kind of ongoing prompt that I'm building piece by piece. And I want to periodically reset that. So in the normal case, I'm going to go prompt tokens. I'm going to take the completion tokens and add them to the prompt tokens. So that would just be, I'll be able to do that with JNP concatenate of just the prompt tokens as they were before, and then the completion tokens. And this only has one axis, or completion tokens. So I don't have to worry about specifying an axis for this concatenate because they're just one-dimensional arrays. And then I actually don't want to do this all the time. I only want to do this when it's not time to reset. So I'll say that, put that in the else, and then I'll say if it's time to reset, which looks like if the step. Okay, I don't want to reset in the 0th step. I kind of want to reset in like the step before we would be at 0. So one way to do that is just say step -1 modulo the num steps per reset, and when that is equal to 0. Another way to do this actually is maybe a little bit easier to think about is if to do step modulo num steps per reset equals num steps per reset -1. So the maximum value that this modular thing could come out with is num steps per reset -1, because once it hits num steps, then it's like it's back to 0. So this means like the final thing before we wrap back around, and that's when I want to do the reset. That's when I want to say, for the next iteration, I don't want the prompt tokens, I don't want to take this completion and add it to the prompt tokens. I want to discard this completion and all of the completions and just go back to prompt tokens equals original prompt tokens. And so that should do the trick. And let's see if it does, or if there are any other issues still to fix. Running this on the TPU, so it should run pretty fast still. Okay, the first completion is still taking a while. Like we said, this is sort of doing a lot of compilation, and we're actually going to see that very dynamically in a second, if this works. I guess I can get rid of this testing model completion later. Okay, so we do have an issue, which is I've assumed there's a batch forward when I'm doing my loss function. And I haven't implemented that actually. So we can quickly implement that, and I apologize for that. Yeah, let's add a batch forward, and we can easily JIT this. JAX.JIT of def batch forward. We've done this sort of thing before. It's just going to take self and byte array batch. This is just for the loss function, so I'll call it byte arrays, and it's going to take byte array of batch size and t. And then instead of returning a float array like this, it's going to return a batch size t 128 float array. That is good. And then how to actually do this, we can just return JAX. This is just a plain VMAP. No need to worry about in-axis and out-axis, just the default thing. The JAX.VMAP of self.forward, which is the one argument version of self of this forward function, where self is already provided, partially applied, and so we'll just pass in the byte arrays. Okay, so this is just revision of something we've seen a few times now. And okay, let me actually get rid of, before I run this again, let me just once and for all get rid of this quite slow viz example from the testing the model completion, because we know that's working now, and we can just go straight to the training loop. So we still need to load the data, initialize the model, and count the parameters. Okay, I've got a typo, surely. Original prompt tokens. Oh, I actually do need that part to be defined. I just commented that. That's my problem. Okay, so, and I'm noticing that I changed the key of tree, so I won't be seeing deterministic. It's another issue. Hold on one second. We'll come to that, but I'm just noticing that I also changed the tree, so this won't be reproducible with the examples that I've seen before. So I'm just going to include that again, and then we will just get rid of the actual expensive part, which is this part, and this part that depends on it. And then this should now be using the same randomness tree as I was using in my testing, but we've got another issue. So num tokens out, did you mean when you were using num tokens? Yeah, of course. So num tokens is not what I meant. Of course, I meant num tokens out. Okay, so we got through part of the first part of the training loop, so we're going well with the batch of with the data batching and so on. In fact, we're training now. The first iteration is always going to take the longest because we have to JIT the whole forward pass, the whole batch forward pass, and the loss function and everything, and the grad. Actually, we're not JITting the grad. Okay, there's another issue here. So array stir, I've just made another typo, but we made it through everything up to that point, so we're getting closer to making it through the whole loop, and hope there's not many more typos. And thank you for your patience. Always takes the longest here because we're JITting the whole forward pass, but we only have to do that once, apart from the fact that when we do the completion, we have to JIT different size forward passes. Okay, here we go. Hey, this is something. And it's done another one. Okay, these are taking a while. These are taking a long time each, and it looks like this is going to take hours to complete. However, we're going to see something cool. See, now we're at the point where we're at the buffer size. And now at the buffer size, it doesn't need to compile it again and again. But for the first few, the sort of buffer was increasing. And now it's even faster because it's done this all before. And so this is seeing sort of in real time what it looks like when you are compiling for the first time versus just executing once you've already compiled, and all of the shapes that you're using are already in the cache. So that is a pretty cool demo, I think. And you sort of saw that in real time. And now it looks like this whole loop is going to finish in like just over 3 minutes or something. Maybe it'll take 4 minutes. And we are starting to, most of the non-printable characters are gone. That's cool. Also, we're seeing that transformer actually learning at the level of predicting the next byte, that some bytes are much more likely than others, or at least some bytes are like a lot less likely. And we're actually seeing something interesting in here in that like many of these look like they're doing a few words and then a few letters and then a space. And so it's like almost like it's learned sort of word length, although there are also some very long words. And there are lots of nonsense words, but there are from time to time some interesting words that look like real. This is almost an interesting word. She, of, short words, it's sort of getting, it might be a bit of a fluke, I'm not sure. We, you, a, but, it should get better and better. And by the time this gets to 2000, I think in my experience, it's like, it's doing okay. And like some of the words are like actually good, including some long words. And I think it eventually prints out Watson, but we'll have to watch closely if we want to see that. And I might have also screwed up the randomness, and then it wouldn't do this. So let's just keep watching, see it getting a little bit better. Full stops followed by new lines. I guess, I don't know if that's a real pattern. I guess this is like wrapped. Oh, that's a M dash. Yeah, that's where the M dashes come from in the LLMs, I suppose. You to could, okay, so it's done full stop space quote and then capital letter. That's pretty cool. Some of this is like BS, but has it done Watson yet? Just have a look through here for some Watsons. I thought it did Watson roughly around here when I did the seeds, so something must have changed with the random seeds, and maybe it's not going to do it. Wades where the world Wimmeting were, and we're back to watching it in real time. But hey, this is pretty cool, huh? Transformer, there you go. So this is almost finished training. I think, let me see. So it would be nice if we could talk about how to JIT this completion loop, but it's a little bit not straightforward. So let's have a think about that briefly. This completion loop from the byte sequence model. This is the chapter that's all about JIT. So, you know, in principle, we should be able to JIT this. And I'm not afraid of marking some things as static. Like, we're clearly going to have to mark the num tokens out as static. Everything else here seems like it shouldn't necessarily need to be static. The hard thing to do is this loop. You know what? Let's just see what happens. It could be an interesting experiment to just functools.partial this and jax.jit marking the num tokens out as static. And we know that we can JIT for loops. We can JIT them no problem. They just take a while to compile because it's going to unroll the whole thing. But in this example, we're actually only doing for loops of length like 8 or so. I forgot exactly how many, like maybe space 1, 2, 3, 4, 5, 6, 7, 8. I think it is 8 bytes at a time that this is generating. We could see if we can just do this static arg names and then worry about the loop after seeing if we get a speed up in the actual execution, if not the compiling, by putting num tokens out. Or maybe this won't be jittable for some reason that I haven't thought of, and then we'll learn something about JIT together. Okay, so let's see if this works. I'm not expecting a massive speed up because a lot of this is already sort of jittered stuff, and the forward pass is really the big thing, and as we saw, that's eventually being jittered, like it's being jittered enough. But yeah, unclear. Once we do this first completion, we'll see whether this JIT is going to work. It looks like it worked. It ran once. Taking a while, but we saw this earlier. This is the same as earlier. It was taking a while. It's putting out nonsense. Actually, it's already starting to put out, I don't know, maybe less nonsense than before. There's a lot of spaces, that's for sure. Spaces are quite common in this data too because every line is indented by 4 spaces, and in the table of contents there's even more spaces. So maybe it just really likes spaces early on in training because it's like a pretty good bet to predict the next character is going to be a space actually. So when we then sample from that probability distribution, we might be getting a lot of spaces. Okay, so this actually worked, and I'm not sure that it was like faster. We should now be hitting the point where we're at about 64 characters and things get a little bit faster. I suppose. Although, actually, the first time we go through, even though this only depends on the 64, the prompt tokens is still growing at this point. So we are still, the shapes of the input, even though like the effective shape of the input is less, we would have to go up and like slice off the last 64 characters, or up to 64 characters of the prompt, and then put it in for this to actually, at this point, do better. But remember, we saw that by the time it got to the end of this, like the first 32 generations or whatever it is, however often it's doing them, it was then generating much faster, and that time, and then like it's done the whole, all these shapes have been done before, and so then it's definitely using the cache. So we just have to wait for this first round of completions to finish. This seems like it's taking longer than previously, but I could be mistaken. I could be just misremembering that. Yeah, it's quite interesting. Now, even after just 27 steps, it is, by the way, not putting out that many unprintable characters. So it's like pretty fast that this model learns that those are not to be printed, which is not surprising, but it is kind of cool. Okay, we're about to hit 32, and then I think we'll reset, and then we're going way faster. Okay, cool. This is good. This, Unclear if this is, yeah, I think this took a longer time. I think we were at like 30 seconds once we started picking up last time, or 30 or 50 seconds or something like that. And so I think this took longer with the compiling because probably of this for loop being unrolled, being like quite expensive to compile. But I could be wrong, and it could be kind of close. But anyway, it's going. It looks to be going pretty fast now, and unclear if it's going faster than earlier, but it is going. Okay, so now how would we go about looking at this loop? This is a pretty difficult loop to scan, and part of the reason that I say that is because have a look here at this slicing operation. First of all, this is a dynamic slice. We have an index in the loop that is kind of like incrementing. It's like data. If we're doing scan, for example, this would be an input, or if we're doing for I loop, this would be one of the inputs to the function. And we're doing a scan. We're doing a slice that depends on fundamentally that value. And we haven't done that before. And actually, JAX is not very happy with that kind of thing, although it does provide tools for using it. What we're going to do is look that up now in the documentation. So I need to look up JAX dynamic slice, and then I'll bring this up momentarily. So JAX dynamic slice, jax.lax.dynamic slice. Okay, so this is basically an operator, while this is still running in the background. This is an operator that takes an array and then an array of indices that are allowed to be dynamic, and then an array of slice sizes. So that's like the length of the slice. So instead of the low high, we have like a low and then length API for the slicing. And then this is going to allow us to like compute the value of that. And so this is basically going to set up JAX to internally do a slice. However, there's a couple of things to look out for, which is that, okay, so the length of the slices has to always be the same for this to work. And so that kind of makes sense, and this is the reason. So when we want the output of this function to depend on the inputs, it can depend on the inputs in terms of where the slice starts. But if you were to have a length of a slice depending on the inputs, that would mean the shape of the slice also depends on the inputs. And that is going to be difficult because then you're going to have a computational graph that the size of some array, the shape of some array is going to depend on the values. And so that's not going to work. But it is going to allow us to have the start indices depending. And so that is nice. And I think there's something else in here about the fact that if you have, for example, like if we tried to do this and we did this like min thing, then because like we are gonna have this issue of potentially having like negative indices. If we want to slice from before the start of the array, then you would have some issue where you were sort of only slicing part of an array. Like in Python, if I just say I want to slice beyond the end of the array, for example, then it's only going to give me up to the end of the array. That's not going to be allowed. And so there's some stuff in here about how slices that sort of hit the boundaries will be handled. So here's an example. Note the potentially surprising behavior for the case where the requested slice overruns the bounds of the array. In this case, the start index is adjusted to return a slice of the requested size. So it's prioritizing very much the size of the slice. And that makes sense because it needs to do that for the computational graph to sort of be well defined. And so here's the example. If we dynamic slice an array X, which is defined like this, as just this sort of 3x4 array, and we slice starting at index 1 and index 1, and then we want 2 and 4 characters respectively, then it looks like what it's saying is we would, let me just see what this actually means. So I think this means we would sort of, in the first dimension, we'd go to array row 1, and then in the second dimension, we'd go to row column 1. And so we're sort of sitting here, and then we want to take 2 by 4, and it looks like that's what you get. If you ask for 2 by 3, that fits, right? So that's going to be 5, 6, 7, and then 9, 10, 11, and that's what we get back. However, if we ask for 4, then that kind of is going to overrun in this axis, and we're going to be bumped back to here so that it doesn't overrun. This is not going to be a problem for us, actually. This is quite interesting that it sort of has this behavior. And it says something here about the behavior being implementation defined, which just means that like they make no guarantees, and it's like you shouldn't rely on exactly this behavior. It's kind of like an edge case that you should avoid, actually. And so, you know, if we're going to use dynamic slices, kind of it's our responsibility to use it well and make sure that our bounds are not being overrun, ideally. Like we should sort of make sure that our program never calls this with those kinds of values. But in our case, we actually want slices of different sizes because we want to put things into the transformer when we're not going to want all of the output when we only have a certain number of tokens. Like when I want to complete 30 tokens, I'm not going to be able to put 64 tokens in. I'm not going to be able to come up with 64 tokens. Although we have this thing where we are indexing into the self-forward window, and we have this thing where if we were to sort of set this up very carefully, we probably could make it so that this was going to be a value that if we, let's say, had a window that was only 30 characters long, we could expand the window beyond 30 characters with another, with 30 characters, we could expand with another 34 characters and do a whole bunch of completion. And remember that the transformer tells us the values, for the next token, that like makes a prediction for all the tokens. So it's going to, in particular, make a prediction for the next token after the 30th. And we could just get that one. And then for all other arrays where we have enough, we could just get the last one. And so we might be able to do this, actually. Let us give it a shot. Yeah, I'm feeling good about this. But it's going to be a lot more complicated. So what I want to do is I want to start by having this version of the buffer be commented out so that we have that as a reference implementation. And I want to then figure out what we're going to have to do to make this have a uniform kind of shape and everything, and using dynamic slices. And then we're going to probably use a scan to actually do the loop. So let me have a think. We could take this as sort of a reference, and then we could also take it as a code to modify. I guess what the natural carry would be this buffer, and indeed that's the thing that we're kind of passing along each time, and also this I. So maybe this is actually going to end up being a for I loop. Oh, the other thing that's passed along is a key, which we sort of fork every time. So I guess the key and the buffer is going to be the carry, and then if I is the only thing that would be the input coming from a range, then we can probably get away with calling that, with using a for I loop. That might be the way to go about this. But anyway, let's focus on figuring out this slicing logic. We basically want to make sure that we're only ever calling the forward pass with a window of length 64, our max context length. And if we are sort of well below that context length, then we need to pad the end of the prompt, and we need to make sure that we only get the generation for where the prompt actually ended. So we might have to have some kind of different logic depending on the length of the prompt or something like that. Let's see how we could do that. So this low index is, I guess that's going to be okay. And I think we can do this in JAX and in JIT, because there is a JAX max operation. We probably can't use the Python one, but I think we can use the JAX one. So if I sort of said low is going to be equal to, I think it's jnp.maximum. Let me just look that up. If we look at the API reference, and we can maybe look up JNP maximum, JAX numpy maximum. Yeah, okay, so this is going to take an element-wise maximum of the input arrays. So yeah, that's what we want. So we've got two input arrays, which are actually scalars in this case, and this is going to end up being our dynamic lower bound. And then we basically want the, maybe we could use high as the sort of, as the real, no, okay, we just want to get actual length of the slice, which we want to be our self.max context length. That's going to be needed for dynamic slice length. And then we need to figure out, okay, we could figure out our window now. Our window is going to be a dynamic slice. Dynamic slice, the operand is going to be the array that we want to slice. So jax.lax.dynamic slice of the buffer. And instead of slicing from low to high, let's slice from low to 64 beyond that, whatever that is. And I think this is going to sort of naturally work in that we were never anyway asking for more than the end of the array. High was always going to top out at num tokens plus I. This should be fine. This is the operand. So the start indices is going to be low, and then the slice sizes is going to be length. And now we're going to get back something that maybe goes too far. So in which cases is it going to go too far? Let's figure that out. So if the, let's say the num tokens in is less than max context length, and I is less than enough to make it more than max context length. So in other words, this is less than max context length. So this maximum gets triggered and we end up at 0. Then we would want the actual cursor to be equal to, I guess, num tokens plus I, which might be smaller than like max context length beyond. It might be, I guess that is high. We're always putting things there. Okay, that seems fine. But when is that going to be an issue? So when we are generating tokens, this won't always be the cursor that we want to put into the forward pass, because the forward pass is going to give us out something that will only go from low through to, I think it might be as simple as just going minus low here, but let me actually figure out whether that makes sense in all cases. And then we would want to, we'd want to put cursor here. So let me just see if that would work. If we had have put num tokens plus I minus low instead of -1 before, or like when we're generating like a bunch of tokens, would that work? Num tokens plus I minus low. Low is equal to num, in that case, low is equal to num tokens plus I minus self max context length. And so we'd be canceling out the num tokens plus I, and we'd get the positive max context length. And max context length is almost what we would want to use here. We just want to put -1 instead. So maybe this is it. Now let's see if this works in the case where this is equal to 0. So when this is equal to 0, then when low is equal to 0, then this just becomes num tokens plus I minus 1. And so for example, if we were to put an array of length 30 in, then we would do a forward pass, and we'd want the prediction at the 30th token. So num tokens would be 30. We'd add I, which is going to be 0 in the first case as a test case, and then we'd -1, and we'd actually get 29. But 29 is the 30th token because we're 0 based. So I think this should work if we put cursor here instead. And this is a dynamic indexing, but dynamic indexing is not the same as dynamic slicing, so we shouldn't be scared of it. This might just work. Let's see. I mean, there might be some horrible issue with this that it's not going to work, but it might just work. So let's try putting this in a for I loop. Okay, so to put it in a for I loop, we need to call this the step, and it needs to take I, which is an int, and a carry as input, and it needs to return a carry as output. And we said that the carry should be of the form buffer and key equals carry, and then we need to make sure that we return also the new carry, which is going to be buffer and key with the updated values by the end of this. And then instead of this actual for I in range num tokens out, we would want to replace this with I guess the final carry buffer key is equal to, I guess I don't need I don't need parentheses there. Buffer key is equal to jax.lax.for loop where we have step, and then the lower bound of the loop is 0 and the upper bound is num tokens out. And I think that was the syntax of for I loop, but I guess I better double check that because I don't use this one so often. For I loop. So lower, upper, body fun. Okay, so I got the order wrong, so that's good that I checked. Lower, upper, and then body fun. And that should be right. And then we don't need the, we do need the init val. So we need the init val also. So I forgot about that. So init val, and I guess this isn't called carry, this is called val, but that's okay. It's going to be buffer key, right? So we've already initialized our buffer up here. And that should be our initial value of the buffer. And then init val equals buffer, and we already have key, which has come in on the parameters to the function. And I think the rest is optional. So let us see if this is going to work. I actually don't know. I haven't run this before. We're going to find out together. Fingers crossed. Ooh, that's a problem. Length of unsized object. What is going on there? Okay, so in the for I loop, let's figure this out. Doing the dynamic slice. Length of unsized object. Where are we computing a len? Okay. There is actually information above. The above exception was the direct cause of the following exception. So what was the inner exception was something about JAX core returning a self, and we have a tuple index out of range. So we had an okay. I don't know enough about the internals of this to know where this is coming from. What could be the issue? Let me just double check the documentation again of the dynamic slice. And it looks like this should be a list of scalar indices, one per dimension, and same here. Or slice sizes should be a shape, which is maybe a bit different. But it might be a problem that I've given this dynamic slice just integers here. So what if I just try and turn this into a sequence of integers, and this one too? And then maybe this is the unsized object that it was trying to get the length of, and that could explain the error. Still an issue. Why is the buffer shape 38? Oh no! Because we're only generating 8 tokens. So I'm gonna have to pad more. But I think that's okay. I think that's an easy fix actually, because we can just add, we can just make sure that this is at least max context length. Actually, we better make sure that it's at least max context length beyond num tokens out, because that is going to be the situation where if we want to Yeah, I'm pretty confident this would have worked for, if the rest of the code is working. This problem wouldn't affect if we had have been asking for like 512 completions. Like 512 bytes of completions with the max context length being sort of lower. But I think it is occurring in the case where we have an operand shape of 38 because we only have num tokens in 30 and num tokens out 8. And then we can't get a slice. Like dynamic slice is bending over backwards to get a slice of size 64 all the time. And it's impossible for it to do that, whether it moves to the end, where it like buffers to the end or buffers to the start, it just can't do it. So that's why it's throwing this error. So I think this is like pretty understandable why this is a problem. And so the question is how to fix it. I think this wouldn't have been a problem if there was room to slide, because we kind of made our code robust to this in that we have a big buffer and we will never ask for more than the end, because that would indicate that we are like putting in a sliding window that includes more than the end, because we're normally sort of asking for what's at the end of the sliding window. And so we probably just have to add some things to make sure that this is at least max tokens length. And then I think it should basically just work if we were to sort of say this num tokens out. If this is less than what would make this of length 64, we should just make it higher. And so let me say padding is equal to num tokens out, which is known statically, so we can do this. Padding should be max of num tokens out and self.max context length minus num tokens in. And then if self.max context length minus num tokens in, that's the number of tokens we would need to make 64 the size of the buffer, because we've already got num tokens in. And so if we concatenated this many zeros, we'd make it exactly 64, or max context length in general. And if we wanted more, then we would want more. But if we want less, then this is going to be the max, and this should work. And then I should call this padding instead. And that will maybe work. I think that will at least solve this issue, but there might be deeper issues. You're getting the live coding experience with Matthew. Okay, yeah, this is another typo. This one is an easy error to fix. Look, num tokens is not defined. That's because I meant num tokens in. Yes, because we were doing the calculations based on this. Could otherwise be num tokens out, but I'm pretty sure this meant to be num tokens in. The anticipation is killing me. This tutorial is running way too long. Hey, that's not good. Those are zeros. Wait, but they're not zeros anymore. You know what? It's actually unclear if this is working or if this is giving it some kind of nonsense data. I think I'm going to need to look at jax.debug.print, right? So this could be a good use of that. But this seems to be going faster than before. It's not going to take 2 minutes to get up to 32, at least. Wow, that's appreciably faster than before. Okay, it's still nonsense. I'm convinced that this is incorrect, but it is compiling. So that's something. I think this is fun. I think we should continue trying to get to the bottom of this, and there will be chapters in the video, obviously, anyway, so people can skip what they're not interested in. But this has made the training loop way faster. By the way, this is not affecting the training, so it's not like the model is learning to do the wrong thing. It's just that it shouldn't be predicting all these zeros after the initial prompt until this point, which sort of indicates that there's some error in the indexing. And so what I want to do is maybe make the maybe make the num steps equal to like 32, so it just has enough time to do like a few of these. And then that should, oops, num steps, is that not right? Oh, equals 32, it just needs to be 32. Or equals without spaces. And then I can add some debug prints here and see what happens. So there's nothing batched here, so this should be actually pretty easy to debug print. And I would like to have the hypothesis that my window and my cursor is lining up as I sort of expected. And then let's just see if that's true. So jax.debug.print window cursor, and the window should be window and the cursor should be cursor. And this is going to happen like 8 times per, maybe I should also print the step. Step window cursor. Okay, let's give that a shot. Rolling up my sleeves, getting dirty with the debugging. Hey, here we go. This is interesting. This is some output. I can understand this. Yeah, it looks like something's gone wrong. Okay, this is good. This is good. We can try and understand this. Let's stop it there. I think we've got enough. So if I scroll back a while, I can see there's some error. The first thing is we have our prompt. That's these tokens, all the way actually here to 32. Okay, it hasn't been able to, oh, you know, it's told us where this is coming from, so that's neat. Haha, okay, there's an issue. This step is not called step. I've been printing a function, that's what I'm doing wrong. And I'm just going to do enough to actually get this past the point where it's generating actual tokens, because I think that will be interesting data. And that's happening after like that's happening after even the second step maybe. So maybe I'll just do like 4 steps. Okay, so this should be more readable. Okay, let's figure out what's going on here. So for example, when the prompt is of length 30, it's these characters, and I is equal to 0, what happens? The index is 29. That means we put this into the model, and we get some generations. What? We get some generation. Oh, haha, I've figured it out. We did not. This code is actually all right. And the problem is here. The buffer num tokens out doesn't account for the shorter thing. So it's grabbing 8 from the end of the buffer, which was, yeah, that's the problem. So what I need like real end of buffer. Actually, I think this should be like deterministic, basically. So the real end of the buffer is, I'm not sure why I was grabbing, okay, it makes sense to grab the num tokens out when we had this invariant. But what I actually want to do is grab everything from the prompt onwards, right? So I always want to grab, sorry, I think I've been talking too fast. Let me take a few steps back and see what I've realized. So look, what we wanted was that this cursor was going to line up with this token so we can get the next token that corresponded to the W in the transformer. And then we wanted to put it here, and we've done that. We've got a next token. It's not a 0. What I was seeing earlier was that like zeros were being appended here, and that looks wrong. But that's not a 0. And then it's continuing. It's adding 32, then 42, then 124, then 106. 32 is a good pick, actually. That's space. You know, this model hasn't even been trained, and it can already, or like been one step of training, and it's already lacking space so much that there was the randomly selected first character in this sampling. But we're still getting this added out. And so what I've realized is that our slicing of the buffer at the end was wrong. It was grabbing like the last 8 things here and appending those. And until the thing is long enough that this contains meaningful information, then we weren't getting any meaningful information out. We were just reading this. And it made sense when the buffer stopped here, basically, when the buffer at one point stopped here to take the last 8 things. But now that we're taking the last 8 things of this expanded buffer, because we had this minimum size buffer problem, that is not right. So we should instead be taking from num tokens in to num tokens in plus num tokens out. And that should fix the problem. Let's test it on 4 steps when we can see what's going on. I'm glad we dug into this, because I think this is going to work now. Cross my fingers. Hey, we're getting nonsense, but we're getting sensible nonsense other than just like nulls. So, you know, that's good. This is good. It's filling it up in order, and then it still hasn't gotten to the point where it's using all 64. Let's keep going for a few steps, because I think then the buffer is going to get more interesting, because it'll get longer, and we just want to visually check that everything is right. What about another 4 steps? That should be enough. I'm glad we dug into this, because this has been like a live example of JAX debugging, which is normally pretty hard. If you're debugging JIT is hard, because you want to put print statements in, they happen at trace time. You want to know what's going on during execution, it's totally silent, there are no side effects. But you can use JAX debug, and we saw that in JIT Dojo, but now we've seen it in reality. And it's a pretty flexible tool. I mean, as long as you can find a version of your model that you can run with like a pretty small kind of input, then it's going to work. So what's going on here? So one thing to notice is this cursor is being clamped to 63, which is what we kind of hypothesized and what we wanted. So that's good that seems to be working. I'm not seeing that this array is like larger. And I'm wondering why we're only generating 4 things through this loop each time, when I thought naively there was going to be 8 of them. But maybe I'm just wrong about that somehow. I mean, it really very clearly looks like it's generating 8 tokens at a time. So not sure about that. Oh, you know what's going on? We're getting killed by matplotlib. Look, this array gets cut off here. So matplotlib is obviously like overriding it. And so what I should do actually is I should temporarily silence that part of the training loop that prompts. I should just replace this for now with this, and then we'll put it back later. So yeah, watch out when you're overriding that you make sure that the last thing that was printed was actually something that you wanted to overwrite. That is a matplotlib foot gun that I've stepped on there. I guess you didn't step on a foot gun. You know what I mean. Here we go. Now we're seeing 0, 1, 2, 3, 4, 5, 6, 7 each time. Okay. Now what I want to see is this array getting longer and longer, but it doesn't seem to be getting longer and longer. Oh, that's okay, because this is window. We're not printing the buffer. We're printing the window. Okay, look, I'm satisfied. I think this is working. Clamping to this thing. This window is clearly losing tokens each time. Look, this 87 was previously, there was a space at the start, and now the 87 is the first character. So we're sliding along correctly. We're clamping to the end. As soon as I think we hit the end, we were clamping to it. So here we have up to 60, and then 61, 60, and that is pointing to this one. And then we get the next token, and 62 is the cursor. And then we get this token, and 63 is the cursor, and then it remains 63. That's perfectly lined up. I can now take this debug command out, which will make things go probably a bit faster. Were there any other debugging things that I had? Yes, I need to now do the animation properly. So if I go down to the plot, then I can restore this and go not num steps 8 and just see if this works. See if, okay, now we know that it compiles, we know that it runs. What I want to see now is I want to see actual sensible output, not these errors coming out. You know what? It would be great if we saw Watson, but I don't know if we're going to see him today. This looks pretty sensible. It's going pretty slow because remember, each time this is compiling with a different prompt size. And it's not a loop, so it's not unrolled compiling. So it's running faster than earlier, and we're going to get to all the way to 31 or 32 in under a minute, and then it will be super fast after that. Okay, look, I think this is one hell of a lesson on JIT and static arguments and compilation and recompilation in JAX. I'm really happy that we got to dig into this, and thank you for sticking all the way through. Look at that. Look at how fast that is going. Like, this is no large language model, but we built it step by step, line by line, apart from the transformer, I guess. But, you know, we've compiled it. We'll do another tutorial on that sometime. It takes a while, but, you know, it's nothing we haven't seen before. And it's not a lot of data to be training a transformer on, but it's looking good. I'm just going to let this go, and I'm going to describe the challenge for today and then wrap up this well overdue wrap up of this tutorial. So the challenge that I had in mind, I think we've had enough of a challenge, to be honest. Working through this jitting this completion code. But if you want an extra challenge and you want to specifically dig into what sort of static arguments are about, try adding dropout modules to the transformer. So, you know, machine learning background, you sort of know what this might look like, but you can just sort of imagine like part of the transformer where it has like an MLP or one of the linear layers or something like that. Try adding dropout, which means when you train, you're going to need one version of the code that is going to have like dropout enabled, and you'll need to know that statically because you'll need to do something different where you randomly ablate some of the neurons. And then at eval time, you want to have all the neurons back, and you want to run through them, and you want to do some normalization to make sure that you're not out of proportion with all of the neurons being on. And give that a shot and see what you have to decide what the API for that is going to look like, what different parameters you're going to use, and how that relates to staticness. But have a go and let me know what you come up with, and I'll see you in the next tutorial. Bye.